Hello, everyone. Welcome to another Stardog Demo Day. We're very excited today as we've got a guest on from Stardog who's going to have a little fun with data. Today's topic is Understanding the Power of a Semantic Layer, Royal Edition. You may know that we have these about every 2 weeks or so, schedules permitting, and this is our opportunity to share use cases, real live demos, and business challenges that we're seeing out in the marketplace that Knowledge Graph solves. So my name is Ingrid Ramos, and I'm a director of marketing here at Stardog, and I wanted to welcome you. Wonderful. I'm going to go ahead and introduce our speaker today. His name is Joe Fagan. Joe has over 25 years of experience in IT, mostly in data and storage, and has held positions at various organizations, including Maxstore, AdaptTech. He led a team at Seagate. He's also been a community advocate director for an open source project. So we're very happy to have him here. At Stardog, Joe is a knowledge graph consultant. And in that role, he really helps customers through a unique combination of graph, virtualization, inferencing, and other tools that the Enterprise Knowledge Graph offers to help enterprise create connected data regardless of where that data resides. Joe holds an honors degree in electronic engineering from Dublin City University and a master's degree in mathematics from the Open University. Joe is based in the UK. So we're doing a little bit of an earlier time here, East Coast, North America time, for our EMEA audiences, so welcome. The structure of today's webinar, Joe will give about 20 minutes of demo, some slides setting the demo up, and then of course Q&A. You can use the Q&A tool on the bottom to ask questions. It organizes them nicely for us, but I will be monitoring the chat as well. Great. This is being recorded. A copy of this recording will be sent to you following the webinar. With that, I'm going to go ahead and turn it over to Joe to get started.
Thank you, Ingrid, for that very generous introduction. Okay, today we're going to have a really quick overview of what an enterprise knowledge graph is, and then we're going to demonstrate with semantic enrichment with a simple data set, and we'll be hands-on in the tools that we use at Stardog. And then we'll have loads of time for Q&A. So this is our knowledge graph right here in the middle here, and it's a layer that sits between people or things that use the knowledge graph and the data itself. So it's a sort of a fabric that sits above the data, and the data is traditionally relational database data, can be NoSQL, and it can be unstructured data like files. So these things here in the graph, these nodes in the graph, can be very much just a direct mapping between tables in the data, and the edges can be joins or attributes in the data. Or they can be things that simply don't appear in the data, that are created, concepts, for instance, that are created, that connect objects in the data. And even these objects can be created as well. So we might have a class of high-valued customers, which doesn't appear in the data as such. And we can have relationships like the relationship between a drug and the DNA of a cell or something like this. So it unifies the data and it presents it back up. Applications can use it like our own applications, like Explorer for visualization, or custom-built applications. We can prepare data, curate data, and hand a beautiful set of training data to AI algorithms. We have integration with Python, so anything that's available from an ML perspective in Python is available to you as a knowledge graph. Use it with Stardog. And also to traditional BI tools like maybe Tableau or Power BI, you can access the data as you would have done when it was in the RDB, but you get the advantage of being able to access the new concepts and the new links and layers, the new joins that exist in the knowledge graph, the semantically built additional concepts. You don't have to throw the fabric over your entire data set. It's called enterprise because it covers every piece of data in the enterprise with like in excess of 100 different connectors to different data sources. But you can start piecemeal and just have a small knowledge graph that addresses one problem on maybe a few tables or a few databases, maybe a recommendation engine, and then grow your knowledge graph and incorporate more and more of your data as you become more familiar and competent. So that's what a knowledge graph is. And then if we, I'll spend just a moment on this to kind of motivate this, where I came up with the idea of doing this demo in the first place. This was a complex problem that a customer had. They make complex things, which they call in their lab information system, they call a sample. So everything is a sample. A subassembly is a sample. A raw material is a sample. So material comes in as a sample. Then it goes through some complex process and testing. And based on the tests, which are often chaotic, the processes are sometimes chaotic. Based on the tests, different activities will happen to the sample. And samples can bifurcate into multiple samples. And sometimes similar samples or samples can combine into a single sample. So finally, when a sample pops out as a finished good, the problem is to trace the ancestry of that sample backwards through the system. It's a frighteningly simple job for a graph database and a horrendously complex job for a traditional LIMS, lab information system. And the output of this is just to show a hierarchy, an ancestry of a sample and how they're related. This is really good for root cause analysis. If at the end of the day you have some samples that experience the same fault mode, you want to ask the question, what process did they have in common? And that's the same question as asking, who is my, if we take two people in the on this webinar and we ask who, if we had the data, we could say, who is our youngest common ancestor? It's frightening to think it might be less than 10, 15 generations. Apparently 100 generations might take us all the way back to 0 or 1 AD. So that's what motivated it. And I thought, well, that question is so like family trees. So we decided we would just take that. We would take a really, really simple data set and a really simple link between items in the data and try to see how do we semantically enrich this. The advantage of doing this is we can talk about semantic enrichment. And usually when you talk about semantic enrichment, either the data is too complex to really convey what we mean by semantic enrichment, or the ontology is too complex. And what semantic enrichment is really a combination of both the data and statements about the data, which we sometimes call a data model or sometimes call ontology. We try to avoid the term ontology because it's kind of grown legs and arms over the past few years with its multiple uses. So this is the data. And we have, for instance, the Queen here and King Charles. And 01 indicates that the Queen has child, King Charles. And let's take another example. 1025 tells me that Harry has a child, Archie. So, and now this data right here on the right is already enriched in a few ways. It's data enriched because we have photographs, but it's also kind of topologically enriched semantically because we know that because we're familiar with family trees, we know what this edge means. We know that this is the child of this, and these are siblings, and we could probably figure out that these are cousins. And so it's already been semantically enriched, but of course this data set is not. So we're going to try to take this data set, map it into a knowledge graph, and see not just what's in the data, but all sorts of other things that we can add to the ontology. So let's revise what we're going to do here. These are statements from the data. Queen Elizabeth has child Charles. In knowledge graphs, we use RDF. So everything is stored as a triple. RDF is more or less encompasses the claim that any fact about the world can be stored as in the format subject, predicate, object. And this is indeed how the data is stored. These are fancily called ontological statements. And they're simply statements about not the data, but they're about the domain of which we speak. And the ontology is very familiar to all of us. If a person is a child, the person is a parent, a grandparent is the parent, and so on and so forth. So these are really simple statements. Now, what does knowledge encompass? Well, if I were to tell, for instance, a child what an uncle is, and ask the child to tell me back what an uncle is, and the child repeated the male sibling of the parent is the uncle of the child, well, I'd be very surprised, first of all. But secondly, I'm not sure they got it. It could be a tell and ask system that they're implementing. But if the child happens to say, that means Johnny is my uncle or Mary is my auntie, then the child has taken the ontological knowledge you've given about domains, applied it to data, and arrived at statement. You'd have to, at this point, acknowledge that the child now knows what an uncle is. So she's taken the concept, applied it to data, and created additional statements about the data. And this is knowledge. This is the emergence of knowledge, and where the word knowledge comes from in our enterprise knowledge graph. Okay, so what I'm going to do now is I'm just going to jump in and do a demo. I'm going to take some raw data, map it to a simple schema, and show you the tools on the way. Then we'll add an ontology or just add simple statements about the domain. We'll visualize it, and we'll end up with democratized data with semantic enrichment. And democratized data simply means it's available to everybody, but not alone. It's not just available, it's explorable by everybody in the organization. Fine, so let's jump into the demo straight away. So I'm going to start. This is our startup cloud. This is our landing page for our 3 applications. And this is how we interact with the entire startup platform, in addition to a command line interface. We have the studio, which is the IDE, the integrated development environment for technical people. We have designer, which allows us to create models and ontologies. I won't use the word again if I can avoid it. And we have our explorer, which is a visualization tool. So I'll jump straight into designer here. And I'm going to create a new project. And I'll call it demo. And create the project. And then I'm going to, first I'm going to do is I'm going to add a resource. Actually, there's one other thing I want to do. I'll call it a different name here. I'll go with that. Okay, fine. So I'm going to add a resource, which is my data fields. Now, these could be virtualized data sources, and we might talk about those later. So I could pick from here and enter a SQL command, which would return a table, or I could simply upload a CSV file, which I'll do here. So I grab my file. That's one resource. This is the file we saw, which is just the members of the royal family, and add one more resource, which is the parent-child relationship, so the link table, sometimes called. And now I'm going to take these, and the first thing I'm going to do is create a class, which is a kind of a hold-all for entities in my data. I'll create a class and call it members, and add some attributes. So if I remember, I had a name, which I'll give it the type of string. I'll add that, and I also had gender out there. So I add that as well. Again, it's a string. I could add integers and dates, various other things, but this is a string. Okay, and I will create that. Now I have this class here. And the next question is, how am I going to map data in my database to members of the class members? So that what I'll do is I'll go to add a mapping and just call it M1. It doesn't really matter. And then I'm going to snap this on to say I'm going to relate this to this class. And then I have to just inform it what the mapping is going to be. So I will say here that, well, first of all, annotations. This is a standard in RDF where this is kind of asking me, what do I want to appear on the center of the circle when I visualize? And I could show its gender or its ID, but full name is the thing that makes most sense. And then as a primary identifier, I'll choose person ID. This is to differentiate similar things or everything. Could use full name, but there might be 2 people with the same full name, so just jump straight in there. And then for this bit, very useful if you have like 50 or 60 columns in your table, you can just use the suggest mapping, and I'll go ahead with the mappings that's been suggested. So I'll say, yeah, they're good. And then I publish the map. Well, actually, I don't need to publish yet, so let's cancel that. So that's what I have so far. At this point, I've only mapped members. Now what I want to do now is create a relationship between members, and we'll call it the has-child relationship. So we'll call it has-child. And the source class is members. Often the source class is, the target is different, but in this case, I have only one class. So, and now what I'm going to do is map this table here to the has-child relationship. So I choose add mapping, give it a name, I'll create that and snap that onto has-child and configure this mapping. So now I'm going to tell, so the parent-child, the has-child relationship is going to map from members to members, and the primary here will be parent ID and the secondary will be child ID. And this is the very simple way of doing complex joins in your tables. I still don't need to publish. So that's all our data. I mean, I could publish immediately. Why don't we publish immediately? So I'll just publish here to this. And I'll choose demo. And that'll be this and this. So I just published now. And so now I can go into Explorer. So if I go into Explorer now to explore the data, then I have to choose my database first. And it doesn't take a lot of imagination to imagine what I'm going to see. Excuse me, did I correct? No. They are all the instances I'm connected to around the world. I'm not sure I caught that correctly. 1 second. Okay. Fine. So let's explore our knowledge. We have only one class. We can explore that class. We have members, and we can show instances of members, and we should have all of the instances that is in our data set, and indeed we have. And we can look at one member, say Harry, and see what we know about Harry. And we have the has-child relationship. So these are his parents, traversing that backwards, and these are his children. So that's basically just mapping in the data as it stands. But now let's try to do something a bit more sophisticated. So we'll go back to designer and think, imagine if there's a part of your organization that doesn't like the term has-child, because, different parts of your organization would like to use different terms, and these are really semantic. So, the simplest possible would be just to change has-parent, create a has-parent relationship, which will map members to members. And now we're going to create that. How are we going to populate it? Well, we could use this, but let's use a rule to populate this, because we're talking about how simple it is to create these rules. So a good rule for this would, let's call it has parent. It doesn't really matter what I call it here. And then a rule for this would be, well, if member 1 has a child, member 2, then it makes perfect sense to say that member 2 has parent. Now, as naive as this is, it's the first step in creating a semantic layer. So we've simply said that this relationship is the inverse of itself. Oh, sorry, these two relationships are symmetric, are inverses of each other. So we've added that rule to the database, to the ontology, let's say. And we could jump out, and you can imagine that I'll have the has child and has parent. But what we could do is just add a few more little goodies to this. So I'm going to add another relationship, which could be useful, like has sibling. That's a brother or a sister. And we're going to map from members to members. And we'll create that. And what would the rule look like for sibling? I'll tell you what, let's skip adding that rule for a moment, and we'll add maybe has grandmother. That's a simple one. Has grandmother. And we map from members to members. And let's create that rule. So the grandmother rule might look, it's not difficult, but we expect it'll look something like this. So if I have a parent, and I can use the either has-parent relationship or go backwards along the has-child, it doesn't matter. So I have a parent, which is a new instance. And that parent, member 2, also has a parent, member 3. And what else? So this is a child. This is me. This is my mom. This is my mom. This is my grandmom. Well, I want to make sure that for grandmother, I want to do one other thing. I want to make sure that her gender is set appropriately. So down here to attributes, and I can set the value equal to female. And then what do I want to infer? When I see this pattern in the graph, I want to refer that member 1 has grandparent, or has grandmother, I should say. Member 3, I hope that's correct. Great, and we'll save that rule as well. Oh, I need to give it a name. Has granny. Okay. Perfect. Okay, so I mean, for completeness, we'll just add one more rule. In fact, I've done it out here in Designer. I've got a designer that's ready built that I have an additional rule, which is has cousin, has parent, has. And then I publish that to the database. And if I go out into Explorer now, for instance, and I say, just have a look at Harry now, I get, first of all, what I'll do is I'll show you when reasoning is switched off. So now I'm seeing only the data. So this is only the data that's in the database. The has child, the members. Whereas if I switch on reasoning and then have a look at Harry and see what we get. Throw him into the graph. And we get this semantically enriched view of Harry, where we get to see his siblings, his parents and children, or sorry, his parents and his children. Sorry, his cousins. So there we go. That's what semantic enrichment actually means. So I'll just jump back into the finish the make some comments about these slides that we have here. It's easy to imagine that this graph is maybe a distribution of goods. So this is containers arrive, distributed to mega warehouses and filter down to mom and pop shops. So that's a delivery mechanism. You could also imagine that there are links between cousins, which means we have alternative routes from source to destination. And then shortest path questions would answer whether we're going the most efficient route. We could also ask questions about whether we have redundancy in the system. Other questions could be, this might be a compound like brewer's yeast, and over here in a graph with millions of nodes, we might have a disease called multiple sclerosis. And we come across a paper that says that the compound brewer's yeast, for some reason, correlates with remission in multiple sclerosis. And we want to find out what is what explains it. And we find out that the compound affects a gene in a particular way, or the expression of a gene, which affects gene folding, which affects certain types of cells in the body, especially in the nerve cells, and that's a disease which we call MS. Now, trying to find all the subject matter experts to make those links is very difficult. But in a knowledge graph, you can simply ask what is the shortest path from one object in your domain to another object. And the example I've given is a real case where it was completely unknown what the link was, and a knowledge graph returns the answer. What else could be? This could be a manufacturing plant. These are raw materials. This process means solder these components onto this subassembly. So these things with the smallest amount of imagination can just represent about anything in your data domain. If I jump out here, we could say maybe in a financial use case, these are actors, maybe let's talk about car insurance. And these are various people who have car insurance claims. If there is a fraud ring, we might identify that certain players, certain actors are just over-connected. Because if I crash into you and hurt your neck and you crash into Jane who crashes into me, that's three people who are just over-connected. And we have the same physiotherapist, for example. They're the sorts of things that knowledge graphs are able to uncover really quickly using various graph algorithms like shortest path and clustering and k-means and all these other algorithms. So even though the example was absolutely trivial, all of the fundamental principles apply. If we make the data vastly more complex and the ontology thousands or millions of lines long, then we can significantly enrich the data. And there we have why it's called a knowledge graph. So from that, what we've seen, so is we took raw data, we created the schema, we mapped the data, we added, and this is the exact process. It might take a little bit longer for your organization, but we can end up with democratized data that expresses concepts, ideas, relationships, and everything else in the data, in the language in which that department wishes to see it. And in Explorer, we can have different views for different departments of exactly the same data using entirely different semantics. And that's about, so finally, we take physical or virtual data sources. We don't have to materialize stuff into the graph, we can virtualize. So anytime you touch one of these concepts, it will either pull it from materialized data or it will go out and do the appropriate, say, SQL access to the appropriate table and populate the data. The ontology is normally materialized. We combine those together and end up with a semantic knowledge, a semantic representation of what's in your database. And Ingrid, that's about, let's just jump to questions now, if I may.
Great. In the meantime, I'm also going to pop in another poll about use cases you might be considering. Feel free to select more than one. There also, there's a lot of them there. These are some of our more common use cases in the field now. I wanted to also thank you, Joe. I love this example. I actually, Joe had presented this internally at one of our team meetings, and I was able to go in and do this myself, you know, and I'm a marketing person. So I'm not denigrating my own technical skills here. I'm just saying I didn't need to use SQL or Sparkle. I was able to create the rule myself and then answer these questions. And really my favorite part is turning the reasoning on. So I'm glad you underscored that, because when, you know, it's really easy to sort of understand why semantically enriching data makes a difference for an end user like myself when you switch that reasoning on, and I don't have to go back to the tables and figure out what the column names are and then use pivot tables to try to analyze this data. I'm able to see the connections, you know, almost reverse engineered without having to tap IT. So that's really something I appreciate, and I always love it, Joe, when you highlight that feature. So thank you.
Thank you.
I'm also going to go ahead and go with a question here about reasoning. And we get this question, you know, often. It's a good one. Why do reasoning at query time? What are the advantages, I think is the question here, right? About doing reasoning at query time.
Okay. If I may jump back to here then. It's a great advantage to virtualize the sources, so we don't have to materialize the data into the graph. It makes it much simpler. We're kind of an uninvasive fabric above the data. If we start writing and reading data, if we read data and make copies of it, it just irritates all the data owners and stewardship becomes an issue. We simply do like everybody else. We simply read the database. Now, if we touch this node here, which is a consequence of reasoning, well, if we don't have the data, we're not able to do any reasoning on it just yet. So we need the data first. If we ran standard functions, we'd have to import the data, then run the procedure on the data. And every time we touched a new node or a new piece of data, we'd have to remember to rerun that function on the data. when we express it as rules and inferencing, we can point the ontology at any data set, and immediately those relationships and additional semantic entities pop into life at query time. So there's no housekeeping of creating additional relationships that you probably never need, never touch for that query. So it saves time and it guarantees that we're able to deliver proper virtualization.
Great. And we had some questions in the Q&A and then as well as some questions in the chat. So for those that want to record a copy of this recording, yes, we're recording it. So don't worry, I'll send you to an email. I see also, so we're getting some help from the audience and answering some questions. So I appreciate that. I see Zachary has answered some questions.
If people sign up to stardoc.com and /kits, there's a lot of knowledge kits here, which is knowledge graphs pre-built, simple demo knowledge graphs pre-built. And we in fact have the royal family demo here. So once you sign up, you can deploy that to your Stardoc free instance. Just give it the database any name you like, and you'll be able to deploy that immediately. And there's some more information about exactly what we did today.
Great. And we do have a lot of questions, Joe. You're going to be very happy to see all these OWL questions here and ontological questions. I am going to knock out a couple of questions that I can lump into one here. But, you know, I do see a question about the number of instances, you know, Stardog free. Certainly everyone can get started with that. There are some limitations. There's a version where you can yourself pay monthly, which would allot you, for example, you know, more data, greater amount of data. And then there's an enterprise level. So in terms of the instances, you know, it would really just depend on which level you're on, with enterprise level, obviously giving you more flexibility on the number of instances, et cetera.
Sure.
Okay, so a lot of questions about, okay, you know, for example, can RDFs and OWL expressions show up in Designer? Is the ontology based on OWL2, et cetera, DL or full? And so I know that, you know, there's a lot of deep set ontological questions that can be asked here, but is there a way to speak to some of these questions?
Okay, well, let's talk about OWL first of all. So the complexity of various different, as they're called, profiles of OWL are called various different swanky names, all up to OWL DL, which is full reasoning. We have an interesting history, and that is one of our founders, Evren, wrote the first full OWL DL reasoner called Palette. So we have a rich history, more than a decade in OWL reasoning. Yes, we support every profile up to full DL. So that answers the question. I mean, they're axiomatic statements about reasoning statements. I used what's called the Stardog rule-based system today, which is a much simpler form of reasoning, which says if, then, which is much more kind of procedural code. I wish I could show it to you, but it just simply says, if you find this pattern, then either assert this relationship or assign this class to a member. So that allows you to do many things that people want to do with reasoning, like the simple thing like same as, or inverse, or symmetric, or subclass of, and so on. So you can achieve a lot with our own language. We also support the swirl language. So we have full OWL, or any profile you like. We have swirl, and we have Stardog own reasoning, which is much more intuitive.
And just to circle back to some other languages, questions about Python or Julia, as well as I know there was something here about constraints like shackle. So anything you can, and there it is.
Yeah, indeed, we have full shackle support. Yeah, we have full shackle support. We support all of the W3C languages and file formats associated with RDF. So we have full shackle support, and shackle is often used just to hand beautifully shaped shapes up to your machine learning algorithm. You know, if you want to hand it a bicycle, you want to make it sure it has two wheels and a handlebar. Otherwise, it might break your learning algorithm about you're trying to establish about bicycles. So yes, shackle is quite heavily used in a lot of our ML and AI workloads. Yeah, so we support them all. We support Turtle and Trig and Swirl, all of the W3C standards.
And then let's see if I can throw this curveball at you. I know everyone's talking about Chat GPT, and I guess this is a lot of people are interested in hearing your feedback on this, Joe. And maybe you don't have feedback on it now, but what is your view about AI, such as Chat GPT from Knowledge Graph?
I think it's just mind-boggling to everybody, and the stuff that we can do with ChatGPT is just purely mind-boggling. What we do on the platform we give is really geared towards enterprise data, adding semantic layer, visualizing the data, and it's very, very much working in the real world where you have messy data, siloed data, different types of users, legacy applications, and we're just trying to clean up what you have in your either your warehouse or your data lake or just your storage. ChatGPT is just mind-bogglingly amusing. I think its sense of humor is the funniest thing. I mean, I saw somebody having a chat with asking, do you think a cat would ever pilot a rocket to the moon? And ChatGPT's answers were just hilarious because they recognized that this was a humorous question and kind of went into that domain. We're not quite there. We're not quite ChatGPT. We're not quite ChatGPT. We're an enterprise knowledge graph for the standard organization, business organizations. But yeah, I love it.
I know, it's great. And a lot of AI ML prep, I think that's becoming almost a use case in and of itself for knowledge graph, preparing your data to, deliver tools like ChatGPT and other AL and MI, listen to me, AI and ML. Well, listen, we're going to wrap it up. But if you have any questions, Joe has been very forthcoming with his time and would, be happy to, I think, answer them. On the back end, I'm going to leave you with one last question here while I wrap it up. Team Heir, team spare, or none of the above. I have to have my own sense of humor about things. Mine's not cat humor, I guess it's royal humor, but as always, we all here at Stardog really appreciate your time. We know it's precious. It's your most valuable commodity, except for maybe your data and making sense of that. So please let us know how we're doing. And if there are any other topics that you're interested in hearing more about, I will send an email out with a copy of the presentation, with a copy of the link to the recording. And you can feel free to respond to that if you like. Besides thanking you, I wanted to thank Joe Fagan for his time and his custom created demonstration that he made that we all love internally. And I'm so happy that you shared it externally with our audience as well, Joe. So thank you.
Thank you very much.
And have a wonderful rest of your day. We'll see you at the next demo day. Thank you, everyone.